In 2013, Tomasz Mikolov noticed something wild. He trained a bunch of word vectors. He took the vector for king, subtracted the vector for man, added the vector for woman. The result landed almost exactly on the vector for queen. Computers had learned the concept of gendered royalty by just looking at COOCORN. Nobody had programmed that in. This is the embedding magic trick, and it kicked off the modern era of NLP. Welcome to Lecture 5. 10 videos on how computers learned what words mean by turning them into vectors, and in the process, quietly picked up meaning nobody had explicitly taught them. Lecture 4 gave us the math toolkit, probability, vectors, dot products, counting. Today we watch what happens when you point that toolkit at the specific question: how do you represent a word so a computer can do something useful with it? The answer turned out to be simple, embarrassing even, but it worked. Here's the puzzle for today. A word by itself is not a number, but computers need numbers, so you have to pick a way of mapping words to numbers. Different choices give totally different results, and in 2013, one choice broke the field wide open. Today's 3 beats. First, the magic trick itself. What Mikolov actually found in 2013 and why linguists lost their minds. Second, what the trick actually means, because there's a huge gap between the geometry checks out and the model understands. Third, the full Lecture 5 roadmap, 10 videos on how we got from ID numbers to modern embeddings, and where the story goes next. Beat 1. Mikolov trained word vectors on a big corpus. Each word got a coordinate in 300-dimensional space. Nothing special about 300. It was a common choice. Then he tried something. Take the vector for king, subtract man, add woman. Look at what point in space you ended up at, and queen was the closest word. And it wasn't just king and queen. Paris minus France plus Italy landed near Rome. Walking minus walked plus swam landed near swimming. Hundreds of these worked. The vectors had picked up gender, nationality, verb tense, comparative and superlative forms. All of it from just looking at what words appeared near what other words in a giant text corpus. Linguists lost their minds because for 50 years, semantics, the study of meaning, had been the hardest problem in the field. And here was a Google engineer showing that a plain vanilla neural network trained on Wikipedia had accidentally rediscovered gender, tense, and country capital pairs. Meaning was showing up as a byproduct of co-occurrence. Beat 2. What does the trick actually mean? Careful now. The vectors DO capture something real about how words are used. They cluster by semantic similarity. They rank by relatedness. That is genuinely useful. But the model does not know that a queen is a royal woman. It knows that the word queen appears in similar linguistic contexts as royal and woman. Similarity, not understanding. But similarity is still incredibly useful. For search, you can rank documents by how close their words are to your query. For classification, you can generalize across synonymous phrases. For translation, you can find equivalent words across languages using their vector positions. Similarity is not understanding, but it's often enough. And here's the deep point. The reason the trick works is that we live in a world where words that mean similar things tend to appear near similar other words. That's an accident of the world, not a law of physics. But it's a pretty reliable accident, and Mikolov's 2013 paper showed you can lean on it hard. Beat 3. The Lecture 5 roadmap. 10 videos on the embedding story. Video 2, from ID numbers to distributed representations. The mathematical shift that made everything possible. Video 3, word2vec in detail. What Mikolov actually did. Video 4, GLOVE. Stanford's competing formulation. Same result, different math. Video 5, the distributional hypothesis. The linguistic theory from 1957 that word2vec accidentally validated. Video 6, similarity measures, cosine, Jacquard, and how you actually compare two vectors. Video 7, polysemy, the bank problem, when one word has two meanings and your embedding averages them into gibberish. Video 8, ELMo, the 2018 breakthrough that made embeddings context-sensitive, solving the bank problem in one blow. Video 9, evaluating embeddings, How do you even test if these things are good? Video 10. Recap plus the bridge to Lecture 6. Because embeddings are just the input. To make GPT, you have to stack them into networks. That's Lecture 6. 3 takeaways before the quiz. 1. King minus man plus woman equals queen. Not because the model understands royalty. Because gender, tense, and country capital pairs happen to live as consistent directions in co-occurrence space. 2. Similarity is not understanding. But similarity is enough for search, classification, and translation. Most of NLP runs on similarity. 3. Lecture 5 walks 10 videos of the embedding story, from one hot to context-aware. Then Lecture 6 stacks embeddings into deep networks and gives us GPT. Quiz 1. What did Mikolov 2013 show with king minus man plus woman? A vectors are useless. B. It lands closest to queen. Geometry captures gender relations. C. Word to vec doesn't work. Or D. English has no gendered nouns. B. Queen. And not just gender. Nationality worked. Verb tense worked. Comparatives worked. Hundreds of these consistent directions emerge from a plain neural network trained on Wikipedia. That's the magic trick. Quiz 2. What does similarity is not understanding mean? A similarity doesn't work. B. Vectors capture how words are used, not what they mean, but that's enough for most NLP. C. You need a PhD. Or D only. ELMo captures understanding. B. The distinction is honest. Vectors capture usage patterns, not concepts. The model doesn't know. A queen is a royal woman. It knows queen and royal and woman appear in similar contexts, which turns out to be enough for search, classification, and translation. Most of NLP. Quiz 3. Why does the embedding trick work at all? A. Words have hidden mathematical structure. B. Words that mean similar things tend to appear near similar other words in text. C. Chomsky invented it. Or D. Computers are smart. B. The distributional hypothesis. Firth 1957 said, "You shall know a word by the company it keeps." 50 years later, that observation turned out to be strong enough to build embeddings on. It's not a law of physics. It's an accident of how humans use language. But it's reliable enough to lean on. Back to the puzzle. Lecture 5 is the story of how we started making meaning-shaped vectors. And the whole story rests on one observation from 1957. Words that mean similar things appear near similar other words. Next video we set the stage. Because before word2vec, computers represented words as ID numbers. And that approach had a specific fatal flaw. Next time, the boring numeric representations we used before embeddings. IDs. One-hot vectors. The mathematical shape that made cat and kitten as far apart as cat and banana. And why that had to change. Hit subscribe.